gas at millions of Kelvin, and it is emitting in the X-rays. And you can use those X-ray observations to estimate the mass in gas. And this was one candidate for the missing mass that Zwicky could not see because he did not have access to X-ray instruments. But in fact, as it turns out, even if you estimate the mass in gas, it turns out to be at least a factor 10 smaller than the mass that Zwicky had estimated using the Virel theorem. So the missing or dark matter mass problem did not go away. Okay, so this goes back to the 30s, the optical observations, and this was the first evidence for dark matter. And then there is, I can see raised hands, but I'm not going to answer any questions right now. Please hold your questions until the end. So then there is the more famous evidence which comes from galaxy rotation curves, where you do this even at MSc level. You ask if I have a cloud of matter, and I ask what is the rotation velocity of a test particle at different distances from this cloud of matter as a function of distance. You will find that in the Newtonian framework, if this cloud contains all the matter that there is and it's isolated, then this rotation curve should fall off, okay, as 1 over square root r. And clearly observed rotation curves like this one don't. So then the hypothesis was that there must be some extra mass which you cannot see in the outskirts of these objects. These are very different objects from here, because here you're looking at the entire cluster as one object, and these are like individual galaxies. Okay, so this could be one of the galaxies here also. But typically these are nearby isolated galaxies for which these rotation curves are measured. And this is consistent, saying that there must be some extra mass here is consistent with saying that there must also be some extra mass at the level of a galaxy cluster. Of course, there are other theories which say that maybe you can describe rotation curves, without invoking extra mass. But in the standard picture, we say that there must be some dark matter, which is probably explaining both of such kinds of observations. And there are other evidences. For example, what people did was to try to estimate the mass to light ratio of different systems as a function of the size of the system. So for this one, for example, this is a galaxy size system. This is a cluster size system. So this one maybe will sit somewhere here on this scale. And then this cluster will sit somewhere here between 1 to 10 MPC, 1 to few MPC in scale. Okay, and what you see is that when you compile, so you can see these various mass estimates here. And when you compile these mass estimates, what you realize is that as a function of the size of the system, the mass to light ratio first keeps increasing, but then it flattens out at the largest sizes. And it doesn't go above this ceiling of some upper limit. And this, when you convert it into dimensionless units, so this is in solar mass per solar luminosity. So you can convert it into dimensionless quantities by dividing by the expected mean density of the universe, or the critical density of the universe. And what you find is that such upper limits, or rather upper ceilings, are consistent with an omega matter, which is of the order of 0.3. Okay, and you can similarly ask how much dark matter would you require to explain such kind of observations, and all of these estimates come out roughly in the same ballpark, omega matter of 0.2 to 0.3. And finally, the tightest constraint that we have today comes from the cosmic microwave background. And in fact, the tightest, the most robust observational evidence also comes from the cosmic microwave background. So the tightness of these errors comes from a detailed modeling of the data in the cosmic microwave background. But the argument that tells you that there must be dark matter in the universe is much more robust. It doesn't require you to understand any kind of data analysis techniques. It's a very simple physical argument. The argument says that, if you remember, when I showed you this kind of image before, we said that these tiny perturbations in the temperature, they are at the level of 1 part in 10 to the 5. So that means the density fluctuations of matter here are of the order of 1 part in 10 to the 5. Okay, and then what we see today at these large scales are density fluctuations of order unity or larger. Okay, if you come to smaller scales, these density fluctuations become larger. But even at very large scales, in large scale structure surveys, for example, if you average on, let's say, 50 MPC scales, you will find density fluctuations corresponding to order unity. So the argument then is that I want to go from 10 to the minus 5 fluctuations at the time of last scattering, which is 400,000 years after the Big Bang, or redshift of 1100, to order unity fluctuations today, which is a redshift of 0. Now, in the intervening time, since the redshift has changed by a factor of 1,000, the scale factor has also increased by a factor of 1,000. And I already showed you previously that at least at the very largest scales of the universe, the growth of structure is proportional to the scale factor. You remember we had the growth factor that we calculated, and we said that this is proportional. The linear theory growth factor, go back to last time's slides, is proportional to the scale factor. So the scale factor has changed by a factor 1,000 from this time to this time. So naively, at the largest scales, you should have seen a factor of 1,000 increase in the density fluctuations. So the density fluctuations starting from 10 to the minus 5 would have gone up to 10 to the minus 2, increasing by 1,000. And now you could argue, okay, so there is a big problem here, but then you could argue, fine, who says linear theory is correct at these scales, right? It could be nonlinear growth increases the amount of power. We know that at small scales. Fine, you allow for an increase of power even coming from nonlinear structure formation. It cannot it cannot account for this residual deficit of a factor of 100, which is coming from linear theory. It may at most give you an extra factor of a few. That still leaves a factor of 50 to a few tens, which is discrepant in the observed growth of structure from last scattering to today. Okay, and the only way out is to say that at the time of last scattering, the potential wells that existed must have responded to something in addition to what you see here, which means that there must have been a component of matter which you cannot see, which had already started gravitating much more, and it had created density contrasts which should have been of the order of 10 to the minus 3 at last scattering rather than the 10 to the minus 5 that you observe in the baryonic fluctuations. So this is the evidence from CMB that dark matter must exist, some kind of dark matter must exist. And then a more detailed modeling gives you a number for the matter density contrast, matter density parameter of the order of 0.3. Okay, so this is again just a picture to remind you of the linear perturbation theory power spectrum. And this is the idea that we have, that at very large wavelengths or very small wave numbers, we have a situation where the primordial spectrum of power is maintained. But then as you go to smaller scales or shorter wavelengths, that is larger k values, you see this kind of particular behavior in linear theory. And then depending on the dark matter model, this behavior can continue out to very small scales, or it could get truncated. Okay, and here in the upper panel, upper axis, one is showing the characteristic mass scales associated with these length scales. Basically, you say that if I enclose a mean density of the universe inside a radius given by the inverse of this wave number, how much mass would that contain? And that mass is listed here. So for example, you can see that this is in terms of solar masses. So one solar mass would be somewhere around here at around 10 to the 4 MPC inverse, which if you work it out will correctly correspond to something of the size of the solar system and so on. Okay, so this is an alternate way of thinking about things. So what we would like to discuss in today's lecture is the way other matter evolves in this evolving cosmic web, in which, as we showed last time, these density fluctuations grow and eventually they become fully nonlinear, and you can think of them in terms of either spherical model or the Zeldovich approximation or full n-body simulations. And they organize themselves into this filamentary network and dense clumps of matter, which we call dark matter halos. So this is summarized here in this cartoon picture, where dark matter fluctuations grow into these dark matter halos. And this we already saw. We basically want to solve the collisionless Boltzmann equation, augmented by the Poisson equation to describe self-gravity. Now, over and above this, when you think about what is happening to the ordinary matter in the universe. So this ordinary matter at the time of last scattering has already formed hydrogen. And this hydrogen is a gas, and then there are other species. Helium will also exist, for example. And this gas pervades the universe and it is gravitating. So it responds to the gravitational potential wells created by these dark matter clumps. So everything is happening together. It's just that the dark matter has a head start because it was not held in thermal equilibrium with the cosmic microwave background photons or with the radiation of the universe. So it was allowed to gravitate early on. And at the time of last scattering, hydrogen is abundant and the photons have free stream. So the hydrogen is not feeling any photon pressure anymore. So there are no sound waves. There is no photon baryon plasma anymore. And this hydrogen now starts seeing the existing potential wells, whatever has been created by that time in the dark matter. And this gas will now start condensing into these potential wells. Okay, it will start falling into these potential wells. As it falls into the potential wells, it gets compressed and heated. Okay, because just think about your standard thermodynamics. If I compress a gas, it will start getting heated up if I decrease its volume. But if I heat up a gas, and this gas is made up of atoms, for example, there will be line transitions in the atoms which can get excited. Okay, so these atomic line transitions are things that can get excited. And once these line transitions get excited, what will happen is that this hot gas will start emitting. Okay, to start emitting photons. So the energy that this gas picked up because of its compression will start getting released as the gas radiates. Okay, so once a system starts losing energy like this, it cools because it is losing energy, right? So this is a very nice thing that happens in this framework, where gas initially contracts because of gravity, it gets heated up, and then because of radiative transitions, it starts cooling again. But now the gas is cool and it has become compact. And because it is cool, its pressure has gone down and it can condense even further. Okay, so this can eventually lead to fragmentation and a kind of runaway process where if your cooling is quick enough, if you can get rid of this energy that you pick up due to compression fast enough, then you can reach a stage where this gas, this hydrogen gas, becomes so condensed and so compact that nuclear fusion can get triggered. Okay, so you can form these molecular clouds, and then inside the molecular clouds, you can have fragmentation of clumps, and ultimately stars can start forming. So this is our very, very basic picture of how star formation so how galaxies start forming and how stars start forming inside these galaxies. Okay, so this is a picture that was laid down in the mid-80s or so, and it has been shown to be quite successful. Even at this simple level, it is quite successful. In the details, of course, there are a lot of open questions, and this is a huge, completely open set of problems which people are currently investigating using all kinds of techniques, both observationally as well as using full-fledged simulations. So it's a wide field. I will not have any time to touch upon it, but I will focus on the fact that we understand at least that galaxies form inside these dark matter halos. Then we can ask, okay, if a galaxy is forming inside a halo, what is happening around the galaxy? Okay, so basically once a galaxy forms inside the halo, some things will happen to the galaxy because of whatever mass is coming in and out of the halo. But then other stuff will happen because of the interactions of this galaxy with its neighbors. So basically all the halos, let's say some of the halos, they get galaxies inside them, depending on whether or not the conditions inside the halo are good enough. And other halos, which are maybe less massive, they are not able to condense the gas inside them to the amount where you need, so that this atomic cooling, etc. happens. And in these low mass systems, maybe galaxies will not form. Okay, so this is the kind of picture that emerges. And these halos, as we have seen earlier, they will themselves interact. They may fall into each other, so they may merge and they will accrete more mass. So if isolated halo accretes more mass, chances are that it can produce more stars. So the galaxy sitting inside it could grow larger and larger. On the other hand, if a halo finds itself in a dense environment and it gets like this small halo, for example, it kind of met this big halo and it got eaten up. and it became part of a bigger system. So in this case, what you will have is a larger halo in which there are sub-halos, and inside these sub-halos will be the galaxies that they came with. Okay, so these galaxies will retain their individual identities for much longer than the dark matter halos themselves, because these galaxies are very, very compact objects. Okay, so the dark matter halos can be of the order of a few hundred kpc. The galaxies inside them will be of the order of tens of kpc, less than that. Okay, so our Milky Way, for example, our distance of the sun from the Milky Way is of the order of 8 kpc. The size of the Milky Way is expected to be of the order of 30 kpc in diameter. So galaxies are much smaller system than their host dark matter halos. That is one thing. And the other thing is that galaxies are formed out of gas and stars, particularly, whereas dark matter is just this collisionless fluid. Okay, so the stars are much more compact and they can hold themselves together for a longer period than the dark matter halo, because the dark matter halo can get stripped from its outskirts depending on its interactions with other halos in the group. So this is the typical picture where galaxies individually will form in the potential wells of individual dark matter halos. But then when the halos merge and accrete, these galaxies will form groups of galaxies. Okay, and this is the kind of stuff that you see here. This is a very, very large group. It is called a cluster, where you can have many hundreds of galaxies in this image. Okay, and you can show that they are all gravitationally bound actually to this particular object. All right. So this is a very rapid fire introduction to galaxy formation. And this is a little bit of nomenclature. We will not use all of this, but it's good to know if you delve into the literature and you start reading papers. So as far as the halos are concerned, dark matter halos, there is this overall parent halo in which there can be substructure. So these smaller gray ellipses are subhalos. And right at the center of this parent halo is a really dense clump, which you can think of as the main halo, around which this parent halo accreted all its mass. And then as far as the galaxies inside this are concerned, so the galaxy which lives inside the main halo is the central galaxy of the group. And these other galaxies which live inside sub-halos, they are called satellites of the group. Okay, and sometimes you may have galaxies or halos which are so small that they contain only one galaxy. And then this would be a singleton center. This is the kind of things that people discuss. And here is like a brief overview of the kind of mass and length scales that one is talking about. So for example, the Milky Way has a halo mass, which is of the order of 1,000 billion. So this is like a trillion solar masses, 10 to the power 12 solar masses. Okay, and its virial velocity. So virial velocity, remember, comes from the virial theorem, where you associate a velocity dispersion with the mass and radius of the halo. And actually, if you go back to the spherical model, you will realize that the mass and radius of the halo are related to each other, because the halo must contain, the average density of the halo is of the order of a couple of hundred times the mean density of the universe. So basically, if you know the mass of the halo, you can calculate its size according to the virial theorem. And then the virial theorem will also give you a velocity estimate for the dispersion inside the halo. So if you do these calculations, a 10 to the 12 solar mass halo will have a virial velocity dispersion of the order of 100 kilometers per second. So these are nice numbers to remember. If I go up by a factor of 1,000 in mass, I will reach cluster scales. These will be the most massive objects in the universe. And you can easily show that going up by a factor of 1,000 in mass will go up by a factor of 10 in the virial velocity, because the scaling will be m to the power 1/3. And so from 100, you'll reach 1,000 kilometers per second dispersion. And on the other hand, if you go lower in mass, these are also interesting objects. So by a factor 1,000 here, you will reach 10 to the 9 solar masses with virial velocities of only a couple of tens of kilometers per second. Okay, and these are the dwarf galaxies, which are actually now becoming very interesting from the point of view of dark matter searches. Okay. And here are some other scaling relations which are useful. So for example, this is the spherical collapse estimate of the mass of a halo in terms of its radius, where this capital delta is of the order of a few hundred, like I said, times the mean density of the universe. This part comes from spherical collapse, that the fact that this quantity does not depend on mass. And then this is just a dimensional scaling. So if I know the radius, I can convert it into mass and vice versa. And the virial velocity just comes from the virial theorem like I showed you, and it's given by this. Okay. Now, okay, so we probably don't need to worry about these scalings for the time being. These are just written down. This is like the mean mass. So in a mean density universe, how much mass would be contained inside a radius RL? L stands for Lagrangian in this case. And how is the virial radius for this mass associated with the Lagrangian radius? It's like a factor of 6 lower than the Lagrangian radius. Okay, so Lagrangian radius is the radius which would contain the same amount of mass but at mean density rather than at a density of 300 times the mean. Okay, so this is just again a picture. So this is the framework in which we are working. The large scale structure of the universe is organized into the cosmic web. Galaxy clusters are these massive objects that live at the nodes of these filaments. And Milky Way like objects will be dispersed throughout the cosmic web. Okay, there'll be smaller systems. And there is this hierarchy that you can see because, for example, if you zoom in, so you can see that there is a thick filament here, but then there is a thinner filament maybe here, and the structure here is not very different from the structure here. It's just a scaled down version. Okay, so this is the notion of hierarchical structure formation, where small objects form and then they accrete mass and grow bigger and bigger. And the cosmic web is organized into this hierarchical structure where you have small filaments connecting small nodes, and then they feed into larger filaments connecting fatter nodes and so on. And this is a picture from the Millennium simulation, and this zoom in shows you this particular large cluster where you can very clearly see that it's not just a smooth and homogeneous kind of distribution. There is a lot of substructure, right? There are a lot of tiny clumps hanging all over the place. It is also not spherical very clearly. There is kind of an elongation along the direction of the filaments which feed this object. So all of these things are revealed in full n-body simulations. But it is still useful to think about spherical collapse, etc., because it gives you an analytical insight into how all of the structure is formed. Okay, again, these are just some typical scales. So this is particularly the reason this talk was made was to emphasize some things at small scales. But basically, we are talking about wave numbers of the order of 1 or larger, MPC inverse. Typical Lagrangian sizes of 1 megaparsec, virial radii of a few hundred kiloparsec, and velocities of the order of 100 kilometers per second or so. Okay. Does someone have a question? I can hear someone unmuted. All right. Okay, so when you want to ask how are galaxies connected with dark matter, okay, so the context of the rest of the talk is the fact that you might hear that lambda CDM has problems at small scales, okay, in connecting galaxies to dark matter, and that there are a bunch of problems, missing satellites, etc. So I thought I will give you a brief overview of some of these issues, and it will also allow us to discuss some aspects of the connection between galaxies and dark matter. So one very interesting thing that happens when you try to understand the distribution of mass of dark matter and the distribution of mass of, let's say, stars in galaxies in the, let's say, in the Sloan Digital Sky Survey or in some other survey like Gamma. So these are both surveys. Bernardi et al. 2013 is an analysis of the SDSS, and these green squares are analysis of another large-scale survey. So what is shown here is the number per unit volume, per unit logarithmic mass of the objects that one is talking about. So in the black line, the objects that one is talking about are halos in a simulation. So this is the number density of halos of different masses. So you can see that 10 to the 8 solar mass halos are very numerous, and the cluster size halos of 10 to the 14 solar masses are very few in number per unit volume. But in general, this is the result from n-body simulations. It has a very nice power law-like behavior, and then it starts steepening at large masses. Okay. So now you can ask if, let's say, I want to construct a simple model of galaxy formation in the universe. I could say that let's take all halos of some mass capital M, and this is the total mass in the halo. So I can ask, what is the gas mass in the halo? So the gas mass in the halo will be smaller than the total mass of the halo, obviously, because the halo contains gas and dark matter. And we know from our cosmological model, because we have these parameters omega baryon, omega B, and omega cold dark matter, and omega matter, right? So omega B plus omega cold dark matter is equal to omega matter. So I can take the ratio of omega B and omega matter, which will give me the mass ratio of baryons to total matter when I average over the whole universe. And I could make a simple argument saying that, let's say that all packets of total matter are equally segregated into gas and dark matter by the same ratio, omega B by omega matter. So then if I say for a given total mass capital M or capital M halo, what is the gas mass in this halo? It will simply be this FB times M halo, where FB is this ratio omega B divided by omega matter. And this will be a number like 1/5 or 1/6 in the standard cosmological model. So what has been shown in the dotted line is what you will get for these number densities if you simply take all of the masses and you just multiply them with this factor of FB, which is of the order of 1/5 to 1/6. And it's obvious what will happen.
हम देख नहीं रहे, मेरा ये खत्म होगा, हम थोड़ा सा देखते हैं बाकी.
Somebody is unmuted. Please mute yourself. Okay, give me 1 second. I need to stop sharing and I would like to mute everybody. Okay. All right. So if I just make this point of view that all the mass is segregated according to this cosmic fraction, then the mass function that I would get for gas in these halos is just the original mass function shifted to the left by this factor, FB. Okay. So that is what is seen as the dotted line. And now if I have a simple model in which I say that, or let's suppose all the gas in a particular halo is capable of forming stars, then the mass function in stars should be identical to the mass function of gas that I just determined. So that means the stellar mass function of galaxies in the universe should obey this dotted line. If all the gas is equally capable of forming stars and like all the gas mass gets converted into stellar mass, then I would have seen the dotted line. Now what is shown as the symbols is the result that you get from actually performing the observations in a survey like SDSS and counting the number of galaxies as a function of their stellar mass, the number density of galaxies. And you can see that this, even accounting for very conservative error estimates, you can see that this is nowhere close to the dotted line. Okay, so these two different numbers here, they are referring to different faint end slopes. So the power law is fitted here, and this is a power law with slope something, this is a power law with slope something very different, but neither of these are anywhere close to this. Okay, so that is the big problem. And this is the issue number one, which you need to think about if you want to connect together halos to galaxies. That is, the rate at which you can form stars, the efficiency with which you can convert gas into stars cannot be the same for all masses. Okay, so for example, let's look at this place. Here, I could say that suppose I have an efficiency of forming stars from gas of only roughly 1/10. So only 1/10 of the mass in gas can be efficiently converted into stars. Then I could say that, okay, the number of galaxies that I see of a particular stellar mass will go down because of this. And I can pull this curve lower and I can make it match the knee of this observed stellar mass function with an efficiency factor of roughly 0.1. But it is clear from this plot that this single factor of 0.1 is not able to account for the discrepancy that you see between the dotted line and the observations at all masses, right? So here, for example, you could maybe get away with a efficiency factor of 0.1, but then as you go to lower mass, this efficiency factor must be much more reduced. And similarly, at high masses also, the efficiency must be much more reduced. So the way to, this is a big problem, okay, that all the mass in gas cannot be converted into stars at the same efficiency. So this is the problem of scale dependent star formation efficiency. And the way we currently understand at least the low mass end, there is a pretty robust understanding of the low mass end, which is that, remembers, when stars form, you have already seen courses on stellar structure and evolution. Stars will not just continue to live forever. So once you form a star like the sun, it is not just going to always stay shining forever. The star's life will come to an end at some point. And often this end will happen in a very explosive manner. Okay, a supernova will be formed. And the supernova, as you know, is an event which releases a huge amount of energy in a very short amount of time. It becomes extremely bright. And in fact, the reason that supernovae are so bright is why we can do cosmology with them, which is a different topic. But for the time being, we are just focusing on the fact that the end point of stellar life can be very explosive. And because of this explosive nature, the supernovae that go off in a galaxy can be capable of redistributing mass around them. So they can push things away from them. Okay, gas which is around them can be pushed. And more importantly, the energy that is released can heat up the gas that is surrounding them. Okay, so the idea now is that, suppose there are enough supernovae going off in a galaxy. And enough, what enough means depends on the mass of the galaxy. So if the galaxy is very massive, it has a lot of gas. So then if a few supernovae go off, maybe nothing will happen much to this gas. Little bit heating will happen, but nothing much else will happen. But in a small galaxy, if the same few number of supernovae go off, the small galaxy has much less amount of gas and its gravitational potential well is also much shallower. So a few supernovae going off in a very small galaxy can have a dramatic effect on the gas in their surroundings. And if this effect is dramatic enough, meaning if the gas is heated up to a sufficient degree, then it, as I argued earlier, in order to form stars, remember, the gas needs to condense. And in order for it to condense, it must be capable of releasing its energy. So if a gas which has already condensed is suddenly heated up again, then again it will not be able to form stars very efficiently because it is too hot to condense. Okay, so this is the idea that at the low mass end, feedback, this kind of feedback of mass and energy from explosive events or from winds driven by either these variable stars or more dramatically from supernovae, such effects can lead to a suppression of the star formation efficiency. So this is the regime of supernova feedback at low masses. For high mass galaxies also supernovae exist, but these galaxies are so massive. You see the range of scales here, right? So these are 10 to the 12, 10 to the 13 compared to 10 to the 8. So these are like 10,000 to 100,000 times larger than these systems. So even if a large number of supernovae go off here, they are not going to do much to the gas. So in order to solve the problem of this dramatic inefficiency of star formation at this end, what people had to come up with was this idea that there may be some other source which can lead to a heating of gas at a much larger scale than just supernovae. And one of the promising suspects or promising candidates for such sources is the central black hole in the middle of every galaxy. So the central black hole engine, or the active galactic nucleus, is something which can potentially drive winds and outflows over a very large range of scales. And such outflows are seen in jets, for example, from large galaxies. But it is sort of an open question as to how efficient these jets are in heating up the gas around them. And this is a really interesting and open field of research. For example, Dipanjan Mukherjee, he is giving some lectures. He is also the co-organizer of this school. So if you have any questions about these kind of physical effects of AGN feedback, you should catch him and ask him. He is the local expert on this. Okay, and unfortunately, people like Kandu and Shriyanand are not giving lectures. They would have been the other people who would be able to answer some of these questions. So for the time being, I will just leave you with this, that at this lower mass end, we expect that objects, events like supernovae, stellar outflows, etc., will be important. Also, reionization can affect this low mass end, which is something I don't know whether it will be discussed in this set of lectures or in this school. And then there could be satellite-specific processes, which is the fact that, remember I told you that objects can fall into bigger objects and become satellites of these groups. Now, these satellites are going around and interacting with the hot gas which is there inside this cluster. Okay, and this hot gas can heat up the gas inside the satellite and prevent the satellite from forming stars. So such effects could happen. So at the low mass end, all such kinds of effects are possible. At the high mass end, the only known way that we are aware of theoretically is these AGN outflows, AGN feedback. And the challenge now is to come up with realistic prescriptions for modeling these effects in simulations and in analytical work. Okay, but it's clear that something like this is needed. Otherwise, you cannot explain the formation of galaxies at a much reduced efficiency in a scale-dependent manner like this. But suppose I take some, I use some physical prescriptions for stellar outflow, supernova feedback, etc. And I invent some prescriptions for describing AGN outflows at the high mass end. Then I will have some at least complete physical model. It may be unrealistic, but it will at least be complete in the sense that it will be able to create mass-dependent efficiency reductions across the spectrum of masses. And this is what state-of-the-art hydrodynamical simulations of structure formation do. So this is a slide taken from the Illustris project, where you can see a few different examples in these different colors of different prescriptions for producing these kind of feedbacks. Okay, so at the low mass end, it will be supernova and stellar feedback. The high mass end, there will be some prescriptions for AGN feedback. And the point of this slide is to show you that reasonable models of such feedback are actually now capable of reproducing fairly realistic looking stellar mass functions. So again, the points from Bernardi et al. And from Gamma are shown as the symbols, and you can see that there is a lot of scatter and there's a lot of uncertainty, both in the observations and in the simulations. But more or less, we are matching the trends. And this level of agreement, it's a factor 2 difference here, but compare that to the orders of magnitude discrepancies that we were seeing here. Okay, so this is a remarkable success of current models of galaxy formation. And just to emphasize, what I'm showing you are results of fairly complex simulations, but the basic ideas about these feedbacks and the way galaxy formation may progress in different mass ranges, it is ultimately coming from analytical physical understanding that has been built up over the last 20 or 30 years. Okay, and this is what you're seeing here is the culmination of this understanding. And now, maybe like the last thing that I will discuss today is this idea of these problems that one comes across, one specific problem, and how one might address it in the context of this scale-dependent star formation efficiency. So, just to set the stage, instead of now thinking about n-body simulations, we can think statistically. And we can ask the question, suppose I want to just look at the universe and get a feel for, like if I look at the SDSS, the Solar Digital Sky Survey, right? The galaxies in there. And I look at their stellar masses and how they're distributed and how they're distributed in space also. And I want to get a feel for what is the underlying cosmic web which is hosting these galaxies. So the dark matter halos and how they are connected to each other in filaments, etc. So I can already see filaments in the galaxy structure, right? If I go back to the SDSS image, I can clearly see filamentary networks of galaxies. Now what I'm interested in is tying this up, connecting it to the underlying expected distribution of dark matter. So I can play the following game. I can say that let me come up with a statistical prescription that says, suppose you give me an n-body simulation with dark matter halos. How should I associate galaxies to these halos such that the observed distribution of galaxies is reproduced? Okay, so in simple terms, if I go back to the first slide, what I am doing is I'm imagining in my mind that this SDSS volume is an n-body simulation box with some halos distributed in it. Okay, and now I ask the question, which kind of galaxy should I associate to which kind of halos, and how many galaxies should I associate to a given halo, so that if I do this association theoretically, and then I take that simulation box and I visualize the fake galaxies that I have painted into that simulation box, that visualization should end up looking something like this, because this is the real universe. Okay, so how should I do that? That is the question, and people can have asked this question, and you can do it in different ways. So, for example, one way is on the right-hand side here. It is called a halo occupation distribution, where you say that I will parameterize a functional relation between the number of galaxies in a halo and the mass of the halo as a function of the type of the galaxy, the luminosity of the galaxy. So, faint galaxies, there will be many of them in high mass halos. And in low mass halos, I can have maybe down to very low masses. I can paint in a faint galaxy, and more luminous galaxies. As I go from these -18 to -21.5, I'm going from faint galaxies to bright galaxies. So if I look at very bright galaxies, you can see that I can't paint even a single bright galaxy in these low mass halos. And in the high mass halos also, I can paint only a few galaxies. Okay, so this is trying to reproduce the fact that bright objects are very few in number. Faint objects are a huge amount in number. And the faint objects I can place in all kinds of halo masses. The bright objects I can only place in large halo masses. And this what is shown here is actually the result of a fitting exercise done in such a way that at the end of the day, if I populate a simulation with these kind of numbers of galaxies following from this plot, I will get a distribution which looks very much like the SDSS that I showed you. This is one way of doing it. Another very nice, interesting way of doing it is to say that let us assume that there is a one-to-one relation or an almost one-to-one relation between some property of the galaxy, like its luminosity, total luminosity, or stellar mass, and the mass of the host halo in which that galaxy resides. So in other words, one is saying in this cartoon picture that if I have a large halo, then most likely it has a very luminous, very massive galaxy. And if I have a small halo like this, then it is almost certainly going to have a very faint, very low mass galaxy in it. A large halo having a very low mass galaxy is not very likely. And a low mass halo containing a very large galaxy is almost certainly not going to happen, simply because it may not have had the mass to produce such a galaxy. Okay, so in this way of thinking, one postulates a simple relationship between the stellar mass, let's say, of the galaxy and the host mass, the total mass of the host halo. And what you say then is that the stellar mass I will take from observations from these data points here, and the halo masses I will take from the simulation. Okay, so I will take stellar masses from here, I will take the simulated masses from here, and I will have a list of stellar masses, I will have a list of halo masses in the same volume, and I will say the largest stellar mass I will associate to the largest halo. Second largest stellar mass I will give to the second largest halo. So in this way, I will take all my halos in my simulation and I will start painting them with stellar masses. Okay, so I will create a set of fake galaxies, and that resulting stellar mass to halo mass relation is shown here. And what you can see again is that this stellar to halo mass relation is not always the same steep function. Okay, at high masses, it turns over. And this turnover is happening exactly around the mass scale where you see that this AGN feedback is supposed to start getting activated between 10 to the 11 and 10 to the 12. Right? So this association automatically therefore accounts for this discrepancy, the scale dependent star formation efficiency. And this is one way of statistically solving the problem. And now finally, the last interesting thing that I will discuss today is that you may have heard of something called the missing satellites problem. And there's a related issue which is called the void phenomenon. So the missing satellites problem is the fact that if I look at an n-body simulation and I look at a halo which has the size of the expected host of the Milky Way. So it has a mass of the order of 10 to the 12 to 10 to the 3 times 10 to the 12 or so solar masses. Then in such a halo, here is such a halo, which is this big circle taken from a high resolution simulation. In such a halo, you will see a huge number of tiny halos in the simulation. Okay, a lot of subhalos will exist in this simulation, which will have masses of the order of 10 to the 8 to 10 to the 9 solar masses, let's say. Okay, and 10 to the 8 to 10 to the 9 solar mass objects, halos, are capable of forming galaxies in the standard model of galaxy formation, where gas condenses, then it through atomic lines it starts cooling, and then it condenses further, etc. Okay, so 10 to the 8 solar mass halos are perfectly capable of forming galaxies. There's no reason to stop them from forming galaxies. So now, if I say that let's take a typical Milky Way sized halo in which there are thousands or maybe tens of thousands of subhalos of the order of 10 to the 8 solar masses, then naively I should expect that there should be thousands or 10 thousands of such galaxies also in the surroundings of the Milky Way. But that is not what one sees. If you look at the surrounding of the Milky Way in the local group, you will see of the order of tens to maybe now 100 galaxies. Okay, maybe now the number is increasing with the dark energy survey looking more deeply, or Gaia looking more deeply. But the number is nowhere close to 1,000 even now. Okay, and one expects even more than 1,000 halos. So this was postulated as a problem in the 90s when even fewer number of satellites were known and simulations were already showing that large number of subhalos exist. So the problem was, where are all these missing satellites? Where are these dwarf galaxies? There's a similar issue at larger scales in these underdense voids that I was showing you earlier in the cosmic web. So let me go back to a cosmic web. So for example, here there is a large void, okay? And there are many such large voids in the cosmic web. So in these large voids, there are many low mass halos. Again, 10 to the 9 to 10 to the 10 solar mass halos exist in voids, but the corresponding number of galaxies seen in actual voids in the SDSS is very small. So again, the same problem. This is called the void phenomenon. It's a similar issue as compared to the missing satellites problem, that you expect a lot of faint objects which you don't see. So where are all these objects? So another way of saying it is that if the number of halo mass, the number density of objects with a given halo mass in a certain environment is large, why is the number density of objects with the corresponding value, expected value of that amount of light in the same environment small? And actually, the answer to both of these problems comes from this issue of the scale-dependent star formation efficiency, the mass-dependent star formation efficiency. Okay, so the fact is that if I go back to my stellar mass versus halo mass problem, there is already an issue which says that at low masses, the mass to light ratio, which is another way of talking about the star formation efficiency, is much lower, is much higher than the mass to light ratio at these masses. Okay, so the star formation efficiency is much lower at these masses. So if I am only looking at environments which are dominated by low mass objects, then I cannot just extrapolate based on my standard average picture. I have to allow for the fact that the masses that I'm talking about correspond to a mass to light ratio which is very different. It is very large compared to the typical mass to light ratio. So here, this is the way one can think of this problem. So the explanation within the CDM statistical framework in which the observed luminosity function or stellar mass function has been matched to the halo mass function. The explanation here is that the reason you don't see these faint objects is because the mass to light ratio becomes very large for faint galaxies in any environment. And therefore, in particular in these low density so both in high density environments like Milky Way or in low density environments, the mass to light ratio of faint galaxies is very high. So you will simply not see as many faint galaxies as you might have thought, based on the number of dark matter subhalos that exist. Okay, so for example, another way of thinking about it is that the environment is just inherited from the host. So if I just paint this large mass to light ratio in the environment that I'm talking about, the number of halos that I get will be whatever it is. It will be some large number, but the mass to light associated with that halo will be large. So the amount of light that you will get will be very small. Okay, so this is one way. This is an interesting aspect of the small scales and the dark matter galaxy connection. There are other things. There are other things that are there. Okay, actually, I have removed those slides also. So there are other issues that one can discuss. There's this issue of the core cusp problem and the too big to fail problem, etc. But I will not go into these details now. So instead, I will just stop here and take questions so we can end a bit early. Okay, so let me just first quickly see, because in the chat there is a lot of stuff happening. Okay, so I'll just go through the chat. Let me quickly see. Sorry, where is my? Let me quickly see if there is also something in the. Okay, there is not much here. There's something about the first lecture with Gaussian random fields, but let me first maybe take issues related to galaxies. Okay, so what happens when sometimes a gas is able to escape the halo because of high velocity in a halo merging environment? So these are all issues that one has to account for. Of course, gas will get redistributed in a merger. That's true. And in fact, mergers can substantially change the star formation activity inside galaxies. This is true. So the details are fairly complicated because see, the issue of star formation is complex because of the following. You can have a situation. Suppose I have a merger event. So it's like a train wreck. Okay, all kinds of stuff is sloshing around everywhere. Now, because of this, if gas is heated up, then it's true that it will stop forming stars, at least for some time, until it is maybe allowed to cool again. But on the other hand, it could also happen that during a merger, you could have a situation where fresh gas, so suppose I have a galaxy which has used up a lot of its gas, and now it is forming stars at a relatively low rate, and there is a merger. This merger, depending on the galaxy which is merging, it could bring in some fresh amount of cold gas also. Okay, and if this cold gas comes into the right kind of environment, it might start undergoing gravitational collapse and start forming stars again. So both things are possible, and which one wins out then is a matter of the physics. That is, it's a matter of all the physics that you have put into describing the nature of the gas at small scales, the rate at which mergers happen. So all of that has to be thought of together. And the state-of-the-art simulations like Illustris, for example, have now been doing this for the last few years. They have been studying these kind of problems in detail. Okay, I hope that answers that. Can we make use of dark energy to useful work? Is it seen to be doing so in the astrophysical context apart from gravitational interaction? I am not sure what useful work means. Let me skip over that question. How do we verify the dark matter content estimated from gravitation against another observation in astronomy? So dark matter, if we cannot see it, then the only way that we have to know of its existence is through some kind of gravitational interaction. Now, of course, this interaction could be something that affected the last scattering surface. So like I said, that the cosmic microwave background is another way of estimating the amount of dark matter. So the answer is that the amount that you get from there versus, if you mean astronomy, by astronomy, if you mean something like the local universe, or clusters of galaxies and things like that, then the answer is yes. The amount that you get from both of these kinds of estimates is roughly the same. Okay, so they are consistent. Okay, how does central black hole interacts as in relation to these dark matter halos? So the central black hole is, of course, a very, very tiny object in terms of size. It is massive, but it is very tiny. So there are people who wonder about what happens to dark matter accreting onto a black hole. But as far as I'm aware, the effects of dark matter accreting into the central black hole is not as strong as the effect of baryons accreting into the central black hole. The simple reason is that the inner parts of galaxies or clusters of galaxies are by far dominated by baryons rather than dark matter. So overall, when you average over the entire halo, the amount of dark matter is typically 5 to 10 times larger than the amount of total baryons in the halo. But most of this dark matter is sitting in the middle to outskirts of the halo. Okay, the central parts of the halo typically contain a lot of baryons, because it's the baryons which condense together in the middle and form the galaxy. So they're all concentrated there. And the dark matter is more diffuse, it is collision-less, so it is allowed to be a little more diffuse, and it spreads over the entire halo. So the central black hole, as far as I understand, it's eating up of dark matter. It must be eating up some dark matter, but that is most likely not the relevant quantity to worry about. Okay, the web seems to have grown like branches of a tree and hence can give rise to voids. It seems it could be because of the way matter blew out of the Big Bang. Not quite. This is not anything to do with. Okay, there are two levels of thinking about this question. In some sense, it is related to what happened at least after the Big Bang during inflation, because that is when the seeds of these tiny perturbations which led to large scale structure, that is when they were laid. And the power spectrum that is predicted from inflation has a direct connection to the kind of structures that can form at late times. Okay, so if I had a power spectrum which was very different, the cosmic web that you would see would actually be very different. So in this sense, yes, it does depend on what happens at least right after the Big Bang during inflation. But it is not that that something happened there and it decided the nature of the web that you see today. This web has evolved later. It is still at early times. It has already been in place since redshift 20 or so, the skeleton of the web. And then basically it has been accreting mass and being better and better defined as time goes on. But the structure of the web is related to the statistics of the initial conditions rather than the fact that the Big Bang is pushing everything out. Okay. So how does dark matter halo starts condensing into clumps in the first place? Because total energy must decrease. So how does that happen? And since they do condense, why haven't they condensed furthermore? So they are self-gravitating, right? So gravity is attractive. Just think of it from that point of view. And if you want to think about thermodynamics of gravity, gravity also has negative specific heat. So this is the reason why, unless you have something else, like, you must have seen the classic example of Chandrasekhar limit for a white dwarf, electron degeneracy pressure. It's the degeneracy pressure which is keeping the object from collapsing under the influence of gravity. If there's no degeneracy pressure, or if the mass is too large, then the gravity takes over. So there also a black hole forms, right? And if you do not question that, then you should not question this also, right? So the dark matter halo, of course, can condense because of gravity. It's a very natural thing to happen. The interesting thing is that it doesn't form black holes, okay? It's not, the interesting thing is not that it condenses. The interesting thing is that it stops and it stabilizes. And this is this idea of virialization because of random motions inside the fluid elements inside the clump. Okay, fine. Central black hole in galaxies are gobbling up visible matter. Does it mean visible matter of the universe is decreasing? Well, strictly speaking, I guess yes, because the black holes are gobbling them up. But if you can go back and look at the previous other lectures which have talked about these high energy processes, somebody might have talked to you about Eddington rate and these black hole accretion rates. So try and calculate, you take the central black hole in the middle of the Milky Way and ask how much mass is it accreting, and how much time will it take for it to create a substantial, to accrete a substantial fraction of the total mass, baryonic mass of the universe. I think this will be a very, very long time. So I think this is not something that you will be sensitive to in the kind of observations that you see. Okay, how does central black hole form inside the galaxy forming inside dark matter halo? Sorry, I'm getting distracted by it. Okay, so this is an interesting question, and the evolution of black holes and the evolution of the galaxy. So it's this classic chicken and egg problem, and in fact the question is whether it is a chicken and egg problem or not. Which came first? Did the black hole come first? Did the galaxy come first? Did they grow together? And one very interesting observational fact in this regard is that there seems to be a very tight correlation between the masses of the central black holes and the velocity dispersions of the galaxies in which this black hole lives. And for example, if you think of the velocity dispersion in a galaxy as a rough estimate of the dark matter mass in the galaxy, at least in the central parts of the galaxy, then it means that there is a connection between the black hole mass and the total mass of that system. So larger black holes tend to live in larger systems. Smaller black holes tend to live in low mass systems. And it is a very interesting question as to, can you build a theoretical understanding of this, of how black holes grow alongside their galaxies? Okay, so this is a very interesting observational and theoretical question, which a lot of people are working on. And I don't think there is a conclusive answer yet, but I don't work on this field, so I may also be mistaken, but you should take a look at the literature. Can we associate some temperature to dark matter? The current picture of dark matter says that the temperature is consistent with being very, very low. Okay, so it is cold dark matter. If the dark matter were warm, so hot dark matter is not allowed, because if the dark matter were hot, okay, all of this is in the early universe. Okay, so if dark matter arose from a species which remained relativistic until late times, then it might have been called hot, like neutrinos, for example. If all of dark matter was neutrinos, you would not see the CMB temperature fluctuations the way you see them. Okay, you would have washed out all of those fluctuations. So then you can ask, okay, how low can I make the temperature of dark matter and still keep it at a high level and not spoil the CMB temperature fluctuations? It turns out that because of silk damping, there is a fairly large variation that you can allow. And let's say something like, you can make dark matter fairly warm and still not spoil the CMB. But the problem then happens at later times in something called the Lyman alpha forest, which is a tracer of the intergalactic medium at redshifts of 2 to 4. And if my dark matter is too warm, if it comes down to something like few keV scales, then I will start seeing signatures in the power spectrum of the Lyman alpha forest. And that is in fact the current way that people constrain the mass of these warm dark matter models. Okay, so I hope that answers that. There was, sorry, I have lost the participants. Yeah, so there is a hand raised. So Unique, if you still want to ask, you can please ask.
Hello, sir. Am I audible?
Yes.
Yeah, thank you, sir. So my question was, as you said that dark matter halos, they resulted in the formation of galaxies inside them, and there were sub-halos inside which resulted in the formation of smaller galaxies. Is it possible the dark matter halos are so small that they result in the formation of a single star or something like that? Just formation of a single star?
No, I don't think that is possible, because you have gone through a series of lectures on star formation, right? And you know that single stars do not form in the universe. Stars always form in nurseries where a lot of them will form together, typically, right? So you need those conditions to be met. You typically need globular clusters. So globular clusters will typically form in these giant molecular clouds. So you need things like giant molecular clouds in order for stars to form, right? So you will typically not have individual stars forming. Yeah, I don't think that is a realistic way of thinking.
Okay, sorry. And so my second question was, just like just after the Big Bang, when the inflation process starts, the leptons first annihilated, then the quarks annihilated, and then resulted in. How did the dark matter form in this region? I mean, from where did the evolution started?
So this is an open question, because there are many models of this. So, for example, there are several models of the particle physics of dark matter. So early models said that it could be a WIMP, for example. Supersymmetry has certain candidates for what dark matter particle could be. But the fact is that we have not detected these particles in the lab. Okay, so for the time being, it is a completely open question. And as of now, and also, so direct detection, indirect detection, there have been claims, but direct detection, there has been no conclusive claim, except for one particular experiment, which other people have not been able to reproduce, and the LHC has not seen anything. So it is not at all clear right now what exactly the particle physics of dark matter is. But there are many viable models, and you can analyze these models similarly. For example, if the production mechanism is thermal, just like for standard model, then you can analyze the behavior of the dark matter density as a function of time in the early universe, just like you follow the evolution of the proton number density or the electron number density or something like this. Okay, so the same kind of physics you can apply and say that, okay, I don't know what the mass is, I don't know what the scattering cross section is, but it has to be some very weak scattering cross section with ordinary light, because otherwise we would have seen it. So you can build models like this. But as far as the current understanding is concerned, the situation is wide open. People also look at alternative models like axion-like particles or very light species. So axions are a very different kind of field than your standard model WIMPs or something, or not standard model, supersymmetric WIMPs. So axions can also be viable dark matter candidates. And other people consider that maybe dark matter is not composed of some particle field, but instead maybe it could be primordial black holes. So some fraction of dark matter could be primordial black holes. And right now there are many experiments which are placing observational constraints on the properties of these primordial black holes. So this is a wide open field, and people are welcome to join this field and try to make some headway into either observationally or from the theoretical side as to what this dark matter could be.
So as you explained that the part of this dark matter could be primordial black holes. As from the detection of gravitational waves, the primordial black holes are also capable of producing gravitational waves, which will obviously be of very smaller order. So is it possible dark matter halos can collide and result in formation of this, if they are part of this primordial black holes?
No, what are you asking? Dark matter halos will collide or the primordial black holes will collide?
I mean, if the primordial black holes are produced from this dark matter halos, when they collide, if they produce
primordial black holes are not composed of dark matter halos. You mean dark matter halos may be composed of primordial black holes?
In that case also, if the primordial dark matter halos are composed of primordial black holes, when they collide, are they able to produce gravitational waves?
So dark matter halos colliding, no, you can see, of course, everything colliding anisotropically will produce some gravitational waves. The question is whether these gravitational waves will have any impact on the current detectors, right? And their typical amplitudes and their frequencies will not be in the correct ballpark. So dark matter halos are very diffuse systems. What you need in order to be detectable are compact systems which create a strong enough signal which you can detect. Yeah, so dark matter halos are very diffuse objects. So they are halos colliding it will create gravity waves, yes, but it will not be at the level where you can detect anything. Okay. All right. I don't see any other questions, so we will stop this meeting now. Okay. Thank you all.